record on.
So before you do that, I wanted to find out, is my audio okay or does it sound too echoey? Because I can also mic up.
No, the audio sounds good.
Okay, I'm
Yeah,
happy to put on a microphone if you want.
yeah, no, I can hear you well, and so it should come out pretty well. I usually when I interview people, and it's more so I can kind of watch back through, but I have a YouTube channel that's just kind of, my own. And this way I can embed it in the Universe Today post and just say, here's the interview, like
Sure.
wholesale. So,
Yeah.
so but yeah, it's good we finally got to meet up. I don't think we actually talked during the 2017 eclipse. I remember interviewing you then.
Yeah, I think we talked on the phone, but I don't think we talked over Zoom.
Yes, yes.
Yeah.
Okay.
Yeah.
All right. Well, I'll start in. This is David Dickinson for Universe Today, and I'm here with Dr. Amir Caspi of the Astronomer at the Southwest Research Institute. And in about 2 weeks, we have the last total solar eclipse passing the continental US for past totality till 2044, about a generation.
Yeah.
And we had one in 2017, and about 31 million people are going to be along this path of this eclipse for totality, and probably a comparable number of people, myself included, are going to be journeying to the path of the eclipse. But there are also several science projects that are going on with NASA, citizen science, and I wanted to talk to Amir Caspi because he's involved in both.
That's right. Thanks for having me.
Okay. Yeah, yeah, I know you're involved with a portion of the experiments NASA has, and it's something I didn't realize till I wrote this time. They have only three of the last operational WB-57 aircraft that are refitted with cameras that are actually going to be chasing this eclipse, and you have some experiments on that.
That's right. So NASA currently flies the only three operable WB-57F jets in the world. That's right. Two of those jets will be flying for the 2024 eclipse coming up in just a couple of weeks. I have one experiment on board, and there are two other experiments from other researchers also flying. The experiment that we're doing is flying an instrument called SAMI, which is a suite of scientifically calibrated cameras that are going to be looking at the sun's corona, the outer atmosphere of the star that is only visible during a total solar eclipse, in lots of different wavelengths, but very specifically, we're going to be looking at it in special wavelengths of infrared light. When I say wavelengths, of course, some people might think of those as colors. When we talk about visible light, we say colors, but when we talk about infrared or ultraviolet or X-rays, we usually use the word wavelengths, but it kind of means the same thing. And our cameras for 2024 are going to be looking at infrared all the way from right where it meets the visible light, all the way down to a range of wavelengths that we call the mid-wave infrared, which is the same wavelengths of light that, for example, you and I would glow if we were looking at ourselves with one of those thermal cameras. And very, very few observations of the sun have actually been made in infrared because it's so difficult to do from the ground. Our atmosphere blocks infrared, our atmosphere emits infrared. So it's really difficult to do it when you're on the ground and you're looking through all of that atmosphere. But by getting up to an altitude of 50,000 feet with the WB-57s, that's higher than any commercial airliner. And we'll be able to be above 90% of the atmosphere and 90% of the water vapor that's blocking a lot of that infrared light. So we'll be able to make new observations that very few people have done before.
Now, you did this in 2017. What kind of lessons learned were paid forward, and what kind of results from the initial eclipse chase did you get?
Yeah, our 2017 experiment was basically a pioneering engineering run. It was the first time that the WB-57s had ever been used for eclipse observations. And we were using an older version of a similar kind of camera. It had a visible light camera, which was not a scientific camera. It was really more like a video camera. And it had a scientific infrared camera that measured in these mid-wave infrared light that we talked about. We didn't really know what we were going to see. prior to our flight in 2017, the last time that I know of that somebody had done midwave infrared measurements was back in the 1990s when a
Interesting.
colleague of ours, Jeff Kuhn, flew an infrared spectrometer on a C-130 airplane. And since
Interesting.
then, I don't know of any other observations. We in 2017 made the first high resolution observations in midwave infrared, high spatial resolution. So, really fine pixels. We didn't know what we were going to see.
Yeah.
And one of the things that we saw that was really interesting was that there were two kinds of structures in the corona that were about equally bright in infrared, but they have very different physics going on. Those two structures, one of them is called an active region, which is the corona that's above a sunspot. It's basically a really magnetically complicated region, and the plasma, the ionized gas that's there in that active region, it has temperatures of a few million degrees. And it was glowing pretty brightly in the infrared, which maybe you'd expect that, things that are millions of degrees should be pretty bright
Yeah.
usually, right? But on the other side of the sun, there was something called a prominence. If you've ever seen a total solar eclipse, you've probably seen prominences. They're those red loopy things that you
Yes.
see right above the solar limb. Now, that's material from right above the solar surface that's sort of bubbled up into the corona and suspended there by the magnetic fields. But it still has the same temperature that it did back when it was near the solar surface. And that temperature is only about 10 or 20,000 degrees Celsius, or maybe 30,000 degrees Fahrenheit. Now, that's hot to you and me, but it's obviously about 100 times colder than the active region
Yes.
and the rest of the corona. The corona is just millions of degrees all over the place. So you have two structures that are different by about a factor of 100 in temperature, but they're both glowing with roughly the same brightness in this midwave infrared. You know that the physics has to be different for why they're glowing. And we want to better understand what are the processes that generate that infrared light in each of those different structures. So that's what our new instrument is going to help us understand by being able to see more wavelengths, more colors of infrared.
So is this addressing, I know there's a mystery about the coronal heating problem about why the corona is so much hotter than photosphere. Is this looking to address that mystery?
Yeah, that's one aspect of it. That's
Okay.
right. That's right. The corona, as we said, is millions of degrees. The surface of the star is only about 6,000 degrees.
Yeah.
So how does that happen? How
It
do you
seems
get hotter?
counterintuitive. Yeah.
Yeah, how do you get hotter when you're moving away from what you think is your heat source? And it turns out that the sun's magnetic field is carrying that energy from inside the star and the surface out to the corona. And then it deposits that energy in the corona. But there are many different ways that that could happen. And we want to better understand the mechanisms, the processes, how that magnetic field can dissipate the energy in the corona. So this is one aspect of it. There are a few other things that we're going to be doing. These cameras, they take images 30 times per second. So we'll be able to look at fast dynamic things in the corona, like little jets coming out or
Yes.
waves propagating in the corona. And all of those are markers of different types of processes that could also be leading to heating and could also be leading to how the sun's solar wind is formed. The solar wind is this constant stream of particles that's always coming off of the sun. And we know that it should exist, but it is faster than what you think it should be. It gets accelerated on its way out of the sun. And we're not quite sure how,
Yeah.
how that acceleration happens and how all sorts of turbulence gets injected into that solar wind because we can't see where it's born right in the low corona. That is visible during a total solar eclipse. So hopefully our new observations will help us get a better handle on that too.
So what kind of intercept speeds we're talking about? I know the umber of the moon is going to be moving pretty quick, the shadow of the moon.
Yeah, that's right.
So
At its slowest, basically over the point of greatest eclipse, which happens near the coast of Mexico, near Mazatlan. It's like a little bit inland from that. The shadow is moving at approximately 1,560 miles per hour over ground. The airplanes are going to have an equivalent ground speed of approximately 420 knots or about 480 something miles per hour equivalent ground speed. So they definitely can't keep up with the shadow. They're
Yeah,
not like a supersonic jet,
yeah.
but they'll be able to get about 40% more time in totality. So for someone on the ground who's standing still, they would get about 4 minutes, 27 seconds. The airplanes should be able to get more than 6 minutes, 20
So it's going
seconds.
to extend your observation time.
By 2 minutes or more. That's right. Yeah.
Yeah, I know they chased one in the 70s with the Concorde. They actually did do a shadow intercept. I think it was over Africa. There's video on YouTube that's quite fascinating, actually. You can still see the experiments they did for that. Yeah. There are
If you
also
speak French, that's right.
yeah, obviously. But there are also two missions we didn't have in space they're trying to solve the same mission right now. The Europeans have Solo, but that weren't there in 2017. They launched since then.
That's right.
There's Solo and there's NASA's Parker mission. So I don't know how in contact or how much you're working with those teams. I imagine they're going to be uh, would those kind of observations from those missions complement what you're doing now during that 6 minutes when you get to look at the same kind of path of the corona and what's going on?
Absolutely. So we have co-investigators on Parker and on Orbiter on our team. And Parker and Orbiter are actually going to be in a very unique position for this eclipse, a really advantageous one. So, we're going to be looking at the sun this way, and
Yes.
Parker Solar Probe and Solar Orbiter are actually going to be looking at the sun this way. They're going to
Ah,
be
okay.
near what we call quadrature, where they're about 90
Yes.
degrees apart in the orbit. So the really cool thing is we're looking at stuff on the solar limb, right? Where we can see things
Yes.
coming this way out of the corona and looking at them broadside. Parker and Orbiter are going to be looking at them basically top down. And now Parker does not have a solar imaging instrument. It has a heliospheric imaging instrument. So it's going to be looking at things coming off of the sun, kind of the same way that we are. But even more cool is it's going to be flying through those things that are coming off of the sun. So the observations that we're going to make during totality, Parker is going to be flying through them.
Yes.
And Orbiter does have instruments that look down at the sun. It has instruments that measure the sun's magnetic field at the surface, and has instruments that measure the sun's ultraviolet emission from things like active regions. So the structures that we're looking at broadside, it's going to be looking at top down. Not in the same wavelengths. We're looking in infrared, they're looking in other wavelengths, but we definitely would be able to combine all of that information to get extra knowledge that we wouldn't get if those spacecraft weren't there.
Interesting. Yeah, kind of like stereo A and B that NASA had. They're looking from different vantage points. Yeah,
That's
that's
right.
kind
It
of
does
cool.
give us kind of a 3D perspective, which is something that we really desperately need that we
Yeah.
don't have these days. Yeah.
So there is a campaign underway for those missions to be watching at the same time, kind of compare
I
observations.
believe that's the case. That's right. I don't have direct knowledge that they're planning a particular observing campaign, but I would be surprised if they weren't, given the nature of this particular event. Yeah.
That's interesting. Yeah. Did you guys? I know there were some ideas. I mean, there was an eclipse in 2017. There's one this month or in April coming 2024. But there's always been some other total solar eclipses year round. Did they do any other campaigns to chase after eclipses, like when they were over South America or anything like that?
So with the WB-57s, no, we did try.
Okay.
The 2019 eclipse, unfortunately, wasn't well situated. That eclipse happened mostly over the Pacific, and so the WB-57s didn't have the appropriate range to get there.
Oh,
The
okay.
2020 eclipse, we really wanted to get to, but COVID
Yes. Yes.
unfortunately canceled all travel at that time. And then for 2021, we really did want to go and deploy from the Falkland Islands to catch the eclipse during sunrise.
That would have been
Unfortunately,
interesting.
we didn't get the funding to do that. And then the most recent eclipse was Australia,
Yes.
2023. As you can imagine, getting the airplanes from the United States to Australia is a fairly expensive endeavor. So again, we unfortunately did not pursue that particular option. However, the next eclipse after this one that's coming up in August of 2026, it's going to
Yes.
cross over Iceland. and southern Spain.
In northern Spain, yeah, yeah,
That's
same.
right. And we are already funded by NASA to go to Iceland with the WB-57. So we're going to be flying over Reykjavik with the airplanes to make observations in 2026 as well.
Yeah, Spain gets one in 26. They're both in August. They're in 2026 and 2027.
Yeah.
So I may try to make my way over there for that one as well.
The
Those could be
27
interesting.
eclipse is going to be amazing. It is
Yes,
6.5 minutes long, which is
yes.
near the longest eclipse you can even get. And the cool thing is, Totality doesn't just go over Spain and North Africa, it goes over the pyramids in Egypt.
Oh, that'd be interesting.
Yeah,
I
if you could just imagine that sight.
Yeah, the only part of Europe that gets it is that little tiny corner of Andalusia, southern Spain, and Gibraltar. So I've been
That's right.
over there several times, and yeah, I think that's where we're going to try. It's going to be a hot one. August in Spain is very hot,
That's right.
but
Yeah. Yeah.
it's gonna be amazingly hot.
Yeah.
Yeah, and you're part of the Citizen Kate project as well.
That's right. So I'm also leading an experiment called Citizen Kate 2024. This is funded by the NSF and by NASA. So it's a joint agency project, and it's really cool. It is what we call a participatory science project, or sometimes you might hear it called a citizen science project. Although you don't have to be a citizen of any particular country to participate in this, you just have to be a human being. And we are deploying 35 teams of volunteers along the eclipse path from Eagle Pass, Texas to Holton, Maine, and everywhere in between. These are not professional astronomers. These are high school students, in some cases, middle school students, university students, educators, retirees, people. Some of them do work in science, but not necessarily in astronomy. Some of them have never touched a telescope ever before. And we gave them telescopes, we gave them cameras, mounts, we gave them computers and software, and especially we gave them training and a uniform set of instructions. And they are going to be making basically a unified set of observations. They're all using the same equipment, the same instructions. And as the eclipse shadow passes over every one of them from Eagle Pass to Holton, they're basically taking that data for us so that we can put all of that together for an hour-long observation of totality.
Interesting. I'm actually not going to be far from Holton, Maine. I'm going to be up toward Presque Maine observing myself. I'm just going to watch them. I know so many people are doing amazing photos and things like that. I'm just hoping for clear skies, actually. So, but
Yeah, I mean, one of the really fun things about Kate is the science. This is not the first time this experiment's been done. The original Citizen Kate experiment in 2017 was run by a colleague of ours, Matt Penn, who was back with the National Solar Observatory at that time, and Bob Bayer, who is from Southern Illinois University in Carbondale. They're running a different experiment this year, the DEB initiative. So they sort of went, this way evolving the Kate experiment. We went this way evolving the Kate experiment. We're addressing next generation science now. We're going to be
yes,
measuring the polarization of light from the corona. So some people, if you don't know what polarization is, light is a wave, right? And it waves kind of like waves on a string. So let's say if that string is waving up and down, we're saying that it's polarized up and down. And if the waves side to side, it's polarized side to side. And different physical processes make light polarized. One process that people know of innately is reflection. When light reflects off of things, it gets polarized like parallel to that surface. And that's why we actually wear polarization filters on our faces a lot. We call them sunglasses, but they're really just polarization filters. And they cut out the polarized light that comes off of, for example, puddles of water in the road or the surface of water when you're fishing, so that you don't see all that glare. Now, in the corona, when you're looking at a total solar eclipse, in fact, you can see the image right behind me. The light from the corona, most of it doesn't actually come from the corona. It's actually coming from the surface of the sun, going out into the corona and scattering or reflecting there into our eyes. And that process makes the light polarized. And we know how that light should be polarized. So when we make a measurement, the really cool thing is what we're looking for is little differences in how the light should be polarized versus what it is polarized, and also how bright is the amount of polarization versus the not polarized light. And the really cool thing with these cameras, every one of the pixels has a little polarization filter right on top of it. Kind of like a red, green, and blue filter, except it's a 0 degrees, a 45 degrees, that kind of thing. And it's measuring it all around the sun, all at the same time. It's not, you don't have to rotate a filter in front of the camera. It's doing it inside the camera. And then we can take all of that and put that information together to measure not just the angles of polarization that the pixels measure, but all angles, because you can mathematically combine them. And that image behind me that you see here, this was done in Australia last year with
That's
these
cool.
cameras, where we took all of the angles of polarization and we mapped them to colors. And it makes a really beautiful, beautiful image, this sort of rainbow corona. Now, that's really more for visualization, but there's a lot of science embedded in this data that's really cool. And we can't wait to dig into an hour-long movie of this kind of stuff from 2024.
Also, going back to the aircraft flights again, I believe you're doing a secondary mission to try to look for volcanoid asteroids near the sun. That's
That's
really
right.
cool to me that they're still doing that in this day and age. I mean, I read The Hunt for Planet Vulcan and how they were looking for an intermaterial planet, but there's no planet interior to Mercury, but the jury is still out on whether there may be tiny asteroids near within the orbit of Mercury and the sun.
Yeah, I mean, the problem is, let's say there are some asteroids there. They're really hard to see because they're
Yes.
probably very small. They're probably very black because they're bombarded with sort of soot, from everywhere. And because they're both small and dark, looking at them with telescopes is going to be very difficult. Not to mention that they're so close to the sun that, if you're doing it from the ground, you have to do it during the day, and then there's all
Yes.
this bright sunlight. And if you're doing it from space, well, most telescopes that are built to look at astrophysical things don't want to go anywhere near the sun. So it's really rare that you have the opportunity to try and do this kind of search. A total solar eclipse is awesome because it gives us this dark sky where you don't have to worry about damaging your instruments by looking near the sun. And for the WB57 experiment that we're running, the really cool thing is we're also looking in the infrared. And there have only been, I think, 2 searches for volcanoids in the infrared before our 2017 mission and now this 2024 mission. And the reason infrared is cool is because you remember I said that you and I glow in these
Yes.
midwave infrared bands. So objects that are hot will be very bright in these midwave infrared bands. And so these volcanoids, if they exist, even if they're very dark in visible light, they should be pretty bright in infrared light. So we have a sensitivity that you can't get with a visible light telescope. Now, we might not see anything, but if you don't see anything, that also tells you something. It tells you that the objects have to be, less than a certain temperature or less than a certain size, because that means that they have to be less than the brightness that we could detect. And that would tell us something, because if they were too small, they also wouldn't exist anymore, because the sun's radiation pressure actually causes these asteroids to basically ablate away over time. There's a particular process for this. So if we are able to set limits that say, well, if they were bigger than this or brighter than this, we absolutely would have seen them, and we didn't. So therefore, they have to be smaller. That might also tell us definitively that they don't exist, or don't exist anymore, because
Yes.
they would have been basically destroyed by now. So there's a lot of cool stuff here. It's not our primary science,
Yeah.
but the
Yeah. Yeah.
data basically comes for free with the rest of our mission.
It's a
So we
long
can't wait for
shot,
people to
but
dig
you
into
could.
it.
Yeah. Have the previous experiments put any constraints on, like, in terms of how faint or physical size, like any what would have eluded detection thus far?
I believe they have. I don't want to speak out of turn because it's
Okay,
not my
okay,
science. So you probably want to speak to an expert on that. And
yeah.
unfortunately, our 2017 data, nobody's had the chance to really dig into that to see if we
Wow,
made any
already.
headway on it. I know it's one of those things where you get lots of data,
Yeah.
but the money runs out, and so you
Huh.
don't necessarily
That
have
sounds
time
like
to
a
look at it.
citizen science project in the making too, to
It
just
could
look through
be.
that data. Yeah, yeah.
It
So
could very well
there
be.
could be
Yeah.
potentially volcanoids hiding in the 2017 data that nobody's interested,
That would be amazing.
or
Yeah.
even an AI kind of assisted project to probably scan through. Would be amazing if they. I know NASA's Mercury messenger on the way to Mercury, they were using the imagers to kind of scout the space nearby to look
Mhm.
for. There's been other surveys before, but
Yeah.
I'm gonna try to screen share something here that
Sure.
came out. I just want for the viewers. I thought this is kind of nifty. There is a. All right, I think I'm sharing
Yeah, I
it
see it.
now. Yeah, there's a company called Predictive Science, and they've done this from several other eclipses. And looking at, I don't know if you've seen this recently. This came out yesterday. I saw it on Twitter. I'll call it Twitter. But they look based on what the solar activity. We're going toward the peak of solar cycle 25 right now, and the sun is very active. There's a lot of sunspots. There's a lot of solar activity. They kind of do a predictive. This is probably what the corona is going to look like come eclipse day. And I was
Mhm.
like, that's a very distinctive. I know a lot of eclipse chasers. You can actually kind of tell if you've seen enough photos of eclipses what year it was based on what the corona looked like. It's
Yeah.
not always the same, and I'm like, that's a very distinctive looking corona. If that's what we're going to get to see. So uh, I just wanted to put that out there. Uh, that
Yeah, and in
that's
fact, one of the scientists who contributes heavily to this prediction is on our WB57 mission team as
okay.
well. Yeah.
Okay. Um, Well, I'll probably start kind of wrapping up here. Dr. Caspi, are you going to go see the eclipse as well? Totality?
Well, that's a very good question. So I hope
Okay.
so. During 2017, I didn't get to see the eclipse. I was actually in Houston supporting the WB57
Oh,
mission
wow. That's
back then. So I saw partial eclipse, but I didn't see totality. Um, this year I'm hoping that I can be in Dallas for totality and therefore get to experience my first real long total solar eclipse.
Yeah.
I did see the one in Australia, but I was also live streaming it at the
Yeah.
time, so I only saw a few seconds. I might have to be in Houston to support the WB57 mission,
Oh,
our
so close.
experiment there. I'm hoping that I'll be able to be in Dallas, so fingers
Yeah.
crossed.
Yeah. I'm heading to northern Maine. This one has special significance because it is the only eclipse in my lifetime passes over my hometown of Mapleton, Maine.
Oh,
So
wow.
I know it's hubris to go to Maine in April. I mean, there could be a snowstorm that day.
That's right.
The weather is, but looking at when we're getting to the point this coming Monday that we'll be at that 2 week point. So you'll start seeing the long range forecast, and we can all start dealing with weather model madness. I always like to call it, where we're looking at, you know, I know most people are going to Texas or Maine, but there are years when you look back through the last 20 years that Texas and Maine were cloudy. So it's
Yeah, yeah, of course.
a 15-20% chance. It's still a chance that it could be cloudy. So
Yeah.
uh, it looks like generally it's going to be clearer to the southwest, and it's going to be cloudier up toward the northeast, but who knows? So I have a little bit of mobility too, so we can move around come eclipse day if we not too far. Maybe if I saw over toward the New Brunswick Atlantic coast, we might dart over there. Sometimes
Mhm.
they get a current off the Atlantic coast and it kind of clears off there where Maine is cloudy. So, but no, it's getting exciting. So
And you know, of course, that eclipses can cause strange weather effects. As the temperature
yes,
cools down rapidly, lots of upper atmospheric winds get set up. And sometimes, even if it's cloudy, the clouds will part magically right
yes,
before totality so that you can actually see it. It's a real strange phenomenon, but it's true. It exists.
yeah. What I saw from North Carolina, the last one at the Perry Radio Telescope Institute there. I remember all the mosquitoes came out right as soon as totality hit. So they were fooled into thinking it was dusk,
Yeah.
and yeah, it's pretty fascinating. But yeah, it's we're gonna start our long journey up to Maine here, handing out eclipse glasses along the way. Uh, starting Monday, we're going to start our drive up. So
Good.
yeah,
Well, I want to make sure everybody knows, all of the data that we're taking with our experiments, both with Citizen Kate 2024 and with the WB57 SAMI experiment, those are going to be publicly available. So after the experiment, we're going to, process the data, calibrate the data. It's all going to be available. So anyone who's interested can come and look at it. And I have to tell you, apart from the new jet experiment, and that's just always a fun thing to do. This is my first time running this kind of big citizen science, participatory science experiment. I have to say, all of our participants are amazing. They're all doing exceptionally hard work. Some of them are just learning how to do this for the first time. We're really, really excited to see what kind of science we're going to get, but we're really much more excited about the experiences that our participants are going to get. One of our goals was to try and engage with underrepresented communities to try and give them a kind of experience that maybe they wouldn't have any other way. And we're also depositing the equipment into their communities. So we're not taking the telescopes back. We're
yeah,
leaving them with the communities so that it can be a resource for those students and for all of those community members for hopefully years to come. And we're really, really excited about the educational and outreach opportunities here. We're hoping that this is a transformational experience for everybody. So can't wait.
it's an exciting time, and it's cool to see these kind of experiments underway. Well,
Yeah.
all right, Dr. Caspi, I won't keep you too much longer, but it's been good talking to you today. And well, your missions will have clear skies, definitely, because they'll be up above the clouds. But I hope you get to the
Certainly the one in
eclipse.
the airplanes will. That's
Yeah,
right.
I hope it's clear for everybody along the eclipse path. But no, it's been great talking to you.
Thank you so much for having me. I appreciate it.